My name's Cyrus. I work at Lawrence Livermore National Lab, and I'm a computer scientist there. I've been there for about 15 years, but I've been working on VisIt for about 12. Like all of the other places, Livermore is also hiring. So I will say it at the beginning of my talk to be the most shameless. So I'm also an associate division leader there, and we have a section of about 80 computer scientists that do multi-physics simulation codes and visualization and things like that. So we're always looking for computer scientists. All right, no shame. We also hire non-computer scientists in lots of other areas. So yeah, but my particular organization is computer scientists. But I could try to put you in touch with other folks. Okay, so what's the plan? So what we're going to do is we're going to do some slides, a little bit of introduction, kind of set the stage a little bit about the history of the project and some of the things to think about before we move into a hands-on. The hands-on is going to be split into 3 different steps. So the first is going to be me kind of doing a whirlwind-ish thing, showing you lots of stuff. And then we're going to slow down a little bit, and we're going to try to do 2 kind of more intentional hands-on things. So the guided tour is the whirlwind. Visualization of potential flow is a little example data set, and we also have an example data set with aneurysm simulation. There's a lot of material here. We won't make it through all of it, but here's the plan: 25 minutes, about an hour and a quarter, and then 30 seconds for questions. No. And if you're looking at my slide deck, you might be thinking to yourself, there's about 50 slides there. How are you going to do that in 25 minutes? So you might be thinking what you just heard me say is, hi, my name's Cyrus, and this is about to get ridiculous. We're not going to do all those slides. So there's a chunk of slides there that are really kind of mirror some of the stuff that Joe said this morning towards the end, and we just put them in there because those are our standard, introduction to visualization stuff. So we won't be doing all 50 slides in 20 minutes. Marta sent out an email with some links. So the thing that you need to remember if you want to get to this place is you go to visitusers.org, which is our wiki page, and you say tutorial or type tutorial or search tutorial, and you'll eventually land there. And just real quick, I want to show you, what it looks like. So there's links to where to download. Oh, I got to get out of this. Sorry. There's links to where to download VisIt and all that. And I know and some of you have had success, some of you haven't had success. I'll be happy to work with you a little bit later. But there's also example data files. So if you click here, there's some links here, and that's where the aneurysm tutorial data is, and that's also where the potential flow tutorial data is, and there's also, these are our standard sets. So in order of importance, I guess, these are the smallest, so if you want to be nice to the Wi-Fi, you can download those first. And then we'll also be touching on these other 2, the blood flow and potential flow simulation. Another thing I want to bring up is a lot of our documentation is on the wiki, but we've also been moving things more formally into our manual. So there's links from the wiki to here, but in particular the hands-on sessions, for instance, the potential flow and the aneurysm, they really have things spelled out here in a very prescriptive way on this. And I'll show you how to get to this again. But if I go too fast and you're not able to slow me down by yelling at me, all this information is here. All right. So visitusers.org tutorial. So the files are hosted at NERSC, and they might not be happy with you guys right now. I don't know, but it's intermittently getting denied. So just keep playing the roulette, and maybe eventually you'll land on it. I should have uploaded them to Cooley. I'm sorry I didn't do that beforehand. Another front matter thing, so we have these example data sets. One of them is this potential flow simulation data set. It's a very, very simple solver model that's built using the MFIM finite element toolkit. And that data is available thanks to Aaron Fisher and Mark Miller of Lawrence Livermore. And I think both of them are going to be here tomorrow for the numerical libraries section, so we're trying to have some parity and connect those sections. The other data set is a simulation we've had for quite a while. That's this aneurysm simulation. And it was simulated a while ago using the Life5 finite element solver. I'm not sure if that link works anymore, but that's courtesy of some folks from the Swiss Supercomputing Center. All right, off we go. So project introduction. Okay, VisIt is a bad name for a project. You know, and I think Jack talked about things starting in the last century. It also started in the last century when we weren't as good at marketing. So if you Google VisIt, you're probably, well, we'll see. We'll see what you get. You know, I get this, okay, VisIt, but I also have this problem, right? You've visited this page many times. If you just Google VisIt, you might not have success. You Google LLNL VisIt, you probably do a little bit better. If you do Google VisIt and it's the first thing that comes up and you haven't used VisIt before, Google knows way, way too much about you. Here's the other thing. Okay, here's the term. So we got two options for the verb here. I suppose one is what I'm doing now, although it's not really socially, but you know, you don't also go to the doctor socially, so that's a little weird. And then two is fully what I expect you to do to me with your bug reports and all these other things. So inflicting bug reports on me, I'm open for that. I have a thick skin. Anyways, enough with the fun of the name. What is VisIt? VisIt's an open source turnkey application for data analysis and visualization of mesh-based data, so like HPC physics simulations. It's an end-user tool for people who run simulations, so people who need to slice and dice their data. It works on your laptop. It also scales up to the largest supercomputers in the universe that we know about. And it's open source BSD style. This fun picture over here, that's actually a data set from 2006. So quite a long time ago, but it's still beautiful and it's still big. So back then it was very heroic to make a picture of that. Now it's a little more commonplace. So VisIt supports a wide range of use cases. You know, I think the way I try to talk about this is, unfortunately, for your average simulation, it's not destined to be on the cover of Nature. So you know, it's really at the will or the whim of the person who ran it. So data exploration is where people spend a lot of time with their simulations, cutting it up, carving it up, asking questions, answering questions, you know, interactively. Sort of the data is at the whim of the simulation runner. There's a lot of tools in there to do that. We also do quantitative analysis. That's important for doing new integrals and things of that nature. So there's features to help support that. Visual debugging. Joe has the best example of visual debugging that he showed this morning, where the propeller disappears in the middle of the simulation. So that's one broad use case of that. We have features here too that we're careful about. If you present the data to us correctly, you know, when you pick on things, it'll tell you the same element numbers and all that stuff as your simulation code, as you expect from your simulation code. So if you get a tangled zone or something, you can use that to pick. Comparative analysis is important too. So this could be view graph norm, where you make two pictures and you use your neural networks in here in your visual system to compare them. So that's kind of view graph norm, that's what we call it. Of course, we support making multiple pictures, but we also have tools that can map meshes onto each other and do subtractions for more of a quantitative thing. And presentation graphics is very important, obviously. We have to communicate results. So we got to make movies, we got to make things for PowerPoint, et cetera, so that's also a very important use case. We have a wide range of plotting features. You know, Joe covered a lot of this stuff in his introduction to visualization, but you know, we have things for doing streamlines, path lines, glyphing operations, which are particularly good for vector and tensor fields, pseudo-color rendering, which is really the bread and butter. That's what lots of people do. Volume rendering, which is like you're sending sort of an X-ray through your data set and looking at it transparently. We have some molecular visualization, although it's very limited. It's not really our forte, but we have some features in there for that. And then we have some other things like parallel coordinates that help you look at data. But again, we're really a mesh-based simulation rendering tool, I guess, or mesh-based rendering tool. So some of these things help you get into the data, but they aren't really the focus. We have a very flexible data model. It's built on top of VTK, as you heard about before. And you know, so we support all kinds of different mesh types. So from the basic uniform grids all the way up to AMR. We also have some support for higher order finite elements through MFIM. And VisIt runs on supercomputers. How does it do that? This is the picture that I show to people who are new to supercomputers to help them understand it. What we want here is this picture on the left, right? This is our full data set. We want it to look like it's one coherent, you know, thing, but in reality, how the computer digests it is over here on your right. So the computer has to split things up because there's not enough memory. It has to use the whole scale out of the machine in a distributed memory way. And VisIt's algorithms are written so that we can put things together and create this coherent picture even though things are distributed. And while VisIt is primarily, the focus of building this tool is primarily MPI-based parallelism, we're also doing threaded processing and mini-core, in particular through VTKM, which was mentioned as a mini-core version of VTK to help deal with performance portability on GPUs or other systems. All right, here's a little bit of history. So it actually started being prototyped before the year 2000, so I can claim that it was last century, although I'm not sure if that's a good thing. So it started at Livermore around the year 2000 to replace an internal tool called Mesh TV. At the time, that was part of the ASCII program of DOE, which then evolved into ASC. And so we were internally focused for a while. We got a product, we switched our users over, and then through other funding streams, such as Office Science funding streams like the SIDAC program, we were able to broaden the use of VisIt and move it fully open source, open develop, all that stuff. So we have ongoing collaborations with lots of different universities and also folks like Intelligent Light, which is a company that helps support VisIt. We also work with Kitware as well. And we just recently released VisIt 3.0, within the last 6 months, but I think it was April. So 3.0 is a big deal. It's a lot of under the hood changes, I guess I would say, but there's also some nice shiny things. So one of the biggest things was porting to VTK 8, and that gave us huge rendering improvements. We fully moved to Qt5. Before that, we've been using a combo of Qt4 and Qt5. We have some Osprey stuff in there. Dave demonstrated some of that in peer review. That's pretty cool stuff. Cinema database output, I'm going to show you a little bit more about that. We have been focusing on this new file format thing called Conduit Mesh Blueprint, and I mentioned VTKM. So the features are great, but a bigger effort and probably a more important thing that we did was update our software process. VisIt's about a 20-year-old project. It's gone through migrations before, from old systems to SVN, and now it was time to get to Git. So we finally figured out all the pieces of the puzzle to make that happen. We're now, hosted on GitHub, so our source code's hosted on GitHub, and we ported all of our old docs to Sphinx, so now our docs are hosted on Read the Docs, which is really nice. So this was a big effort by the team, and I guess I should say we have 8 people at Livermore who work on VisIt. There's probably about another 15 people around the globe who work not full-time, but partially on VisIt. So this was a big effort. And I just want to point you to, so Mark Miller, who's one of the core VisIt team members who will also be here tomorrow, he wrote a blog post with the Better Scientific Software talking about some of the aspects of us refreshing our development process. So I think as a team, we're proud to have been able to do this. It was a big effort. Okay, so we provide binaries for you to get VisIt. Some of those binaries may work, some of them may not work for you depending on your operating system. If you have problems, probably best for us to talk tonight and we can solve some of those problems. I know in particular if you're using Ubuntu 18, it might not work. In the past, we were able to compile on old versions of operating systems and then get the benefit of forward compatibility of the libraries. Well, libraries are getting smarter now and putting their version names in the their versions in the file name themselves, which makes it hard for us to do this. So that means we're going to have to go back to compiling to more platforms. It is installed on Cooley, so I'll show you how to connect to that. And we have a script. We have a script called build VisIt. And this does not only build VisIt, it builds absolutely everything else that VisIt needs to be built. This is a script that's been around for at least 11 years, and it's been our way to actually deploy successfully on these HPC platforms. So that's what we recommend to build the full stack. We're also very interested in leveraging SPAC, but we're not there yet. Build VisIt's pretty battle hardened, so it's going to take us a while to migrate over fully to something like SPAC. All right, there's a lot of file formats. The question is, okay, well, which one do I use? That's a hard question. It depends on the nature of your data, I guess I would say. Usually VTK files are really good because those will definitely work in VisIt. They'll also work in other tools. We have this new thing called the mesh blueprint. I'm not going to talk too much about it. I can talk to you about it maybe tonight if you're interested. But that's a new way that we can write HDF5 files or even YAML files if you want to that have mesh data in them and suck them into VisIt. And we have a manual. This manual has not been ported to Sphinx yet, I don't think, but that extensively talks about writing to different file formats. So if you're in the situation where you have to, you have a custom file format, that's really where you have to go. All right, so to scale up, we have this client-server architecture. Really, we have the viewer, which is the thing you stare at probably the most, and that manages all the state. And then there's different clients that can drive it. So there's the GUI, which we'll also use a lot. There's the command line interface, and you can also do other stuff with Python and Java. And then on the HPC cluster, you run what we call the engine, and that's the thing that scales up with MPI and reads the data, et cetera. And we do this scalable rendering. So again, Dave showed an example of this, but when you think about it, how do you put the pieces of the puzzle together? You do local work very quickly, and you do a compositing operation across MPI to get the final answer. So we do that for surfaces, but we also have scalable volume rendering. So you can build upon VisIt. So we have this plugin architecture where you can write your own file formats, operators, things of that nature. We have Python scripting interfaces, and we have something called libsim, which is basically an in situ library that allows you to use VisIt in your simulation code. So so we think of it as a platform for doing more than just clicking around the GUI. You can actually do some pretty heavy customization with this if you would like. And another thing VisIt's been used for is it's been used to deploy research from the visualization community to users. In particular, the parallel streamline, pathline infrastructure was really developed and researched to help the Fusion community, people doing tokamak reactors and things of that nature. And that's been, handed to scientists through our tool. So that's something we're proud of. In general, DOE's visualization community is a happy bunch. We know each other. We don't hate each other. We're nice to each other. So, we're doing open source, and we're trying to help work together to get to Exascale. So there's really two important things that we're dealing with here. A big one is VTKM. So VTK was started in the 90s, and it wasn't written really in a way that could deal with CUDA or OpenMP or all these other things, right? So now that we have an explosion of node-level parallelism, we need some performance-portable way in order to write algorithms so they can run on all the architectures. And that's the purpose that VTKM is serving. Another big scary thing that's going to happen is that your I/O isn't going to keep up with your compute. So we're also trying to address gaps in I/O performance with in situ methods. So that means linking libraries into your simulation. So there's the Alpine project, which I'm part of, which is an ECP project. And that actually supports peer review, Catalyst, and Ascent. And there's also Sensei, who we work with, which Silvio talked about. So our team is investing heavily in both Conduit and Ascent. And by our team, I mean mainly the Livermore team. But yeah, so I'm not going to talk too much about these other than to say that Conduit's a new way we have to describe memory and hand it over to something like an in situ package. Or describe data in memory and hand it over to an in situ package. And Ascent is a new flyweight visualization, basically library, I guess I would say. So what is Conduit? It's what I would claim to be an intuitive API for in-memory data description. The fastest way to describe it is something like JSON crossed with NumPy, but for C++ and Fortran and Python. Maybe that's not fast, or maybe it doesn't roll off the tongue, but it's fast. It also includes conventions for sharing, say, mesh-based data. So how could you arrange the data so we can understand it's a mesh? And it has I/O interfaces and ways to move things around MPI, et cetera. So it's a pretty interesting capability. Ascent, again, is this easy-to-use flyweight in situ visualization analysis library. It's framed around three things. Give me some pictures, do something to my data, and give me my data so I can do it somewhere else. So it uses Conduit as an interface, and that's how we get our C, C++, Python, and Fortran APIs. And again, it leverages VTKM. We talked about Cinema, and I'll just show you something so you can understand what it is a little bit more. So cinema is one of our extracts in a sense. It's also you can write them out with VisIt. And what it does, Silvio described it, is it renders a whole bunch of pictures. So you can think of making an image database of a whole bunch of different angles throughout time. And what you can get from that is you can get a, it's not perfect, but you can get a sort of pseudo-accurate view, 3D view of things by using this image database. And this particular thing that you're seeing here is a cinema extract. It's a little bit of a crude one, but it was rendered from a simulation that we like to call big laser, tiny box. So this is a Kelvin Helmholtz simulation where there's an interface and a laser hits on the side, and then it radiates out and it rolls up. And this may not be super interactive because we're over the Wi-Fi here, and you guys are all downloading VisIt. Oh, it's not going to happen. But it certainly is much, much more interactive than going, oh, wow, yeah. Well, let's try. Never mind. Service unavailable. See you guys. Downtime or capacity problems. Well, we'll look at it later. Anyways, if you have these images, you can browse through them a lot faster than you can read terabytes off of disk, right? So if you can use something like Ascent or VisIt or even Catalyst to write out these image databases while the simulation is running, you can get something that looks like you can explore it. It almost feels post hoc, but it's just image data. You guys are really, I'm going to get a call from nurse. I'm going to get in trouble.
Sorry, quick question.
Yeah.
How would you Google cinema?
So it's called Cinema Science. Yes, there you go. We're not the only ones who make those errors. Los Alamos made it that time. And so Cinema Science, yep. Good question, though. All right. So that's a little bit of an introduction to, gosh, we're not having an earthquake, are we? Uh-oh. So a little bit of an introduction to the VisIt project. Let me go to the next slide. That's going to fix it. Okay. Well, they'll work on it. So before we start the hands-on, there's 5 things I like to tell people to help put things into context and to help you really think about using VisIt. So these are the 5 core abstractions that we provide in the interface and kind of how we built the tool. All right, you ready? There's 5 of them. And I'm going to hammer them into your head. It's intentional, so you won't maybe be able to forget it by the end of this. So the first is databases. So this is the abstraction that we use of how to get you data. So that could be VTK files on disk. It could also be something like libsim that's pumping data in. So in order to make a plot or anything else, you have to have data behind it. The next are plots. So plots are the things that we see, right? So a pseudo-color plot or something like a volume plot. That's the abstraction of how we render data. The next are operators. Operators are how we manipulate data. This is your slicing, dicing, thresholding, things of that nature. So you can think of them as filters, but filters can be more general than just manipulating data or cutting data. The last 2 are really important, but they're a little harder to describe. I guess expressions is a little harder to describe. So expressions is sort of like a domain-specific language that allows you to take fields that are already in your data set and compose them with some mathematical equations in order to make a new field. So what's an example of this? Let's say you wrote out density and you want mass, but you didn't write mass out of your simulation code. So if we have density per element of your mesh, we can then calculate, say, the volume or the revolve volume or what have you, and we can multiply those 2 together and we can create a field that is now the mass versus just the density. And you can think about composing these things in arbitrarily complicated ways. You can break down velocity fields with trig functions and do fun things. So that's what expressions are. And queries are something that allows you to summarize data. So that allows you to ask something like, what's the total mass of my, in my data set. So queries, you don't always get one number, but you typically, that's the way to think about it. You're doing some data summarization operation versus expressions, which is painting things back onto the mesh. Okay, all right. We got our 5 things. Let's just go through some very simple examples of how these 5 things interact with each other. So the most basic thing you can do is make a plot. So you need a database that gives you some data, say an HDF5 file, and you're going to make a plot of some variable, say density from that. So that's a pipeline that uses those two of the building blocks. Getting more complicated, you can apply an operator. So you want to transform the data, maybe you want to slice it. So we slice it, and now the end of our plot is now going to look at a slice of the full data and plot the density versus the full cube. You can add multiple operators. So you could slice part of it, and then you could elevate it to create topology from the field. And then you can make a kind of mountainous looking plot. So you can, for these operators, or for these different things, you can combine them as various flexible ways. All right, so here's another example. So an expression. So in this case, we get our file, we open it up, and we want to know basically the speed, which is the magnitude of the velocity field, which didn't happen to be in there. So we can define an expression that says, I want the magnitude of the velocity, and then now we can make a pseudocolor plot of that derived quantity, whereas before we just had vector data. Yep?
I have a question regarding the expressions. So what kind of operations do you do, can we do related to the expressions? Can we only do like algebraic expressions, or can we also do conditional statements, or like say derivatives? For example, if we did velocities and we forgot to output vorticity.
Yeah. So the answer is yes. There are if statements. There are comparison operators. There are gradient operators. So now when I say that, there are lots of different ways to take a gradient, right? So
are there like find a difference operators?
Yes, there are, and there's some other ones, but it's never gonna fill everyone's needs. So but the basic gradient's there, and it works on like structured grids, and it does something else for unstructured grids. Yeah. So yeah, and I'll show a little bit of that actually. Okay, so back to what we can do. So if we make a plot, we can query a plot. So the example before, I wanted to integrate, say, we've plotted density. I want to integrate density to find mass, also convolving it with the volume of each cell. So again, our query can give us that one number, X grams of something. And you can get complicated, right? So this just shows using everything. And the end of it, you can do something kind of complicated where you've sliced it, which is effectively a cross-section. You can say, well, now I'd like to know the maximum point on that cross-section, so you can go ahead and get the maximum speed there. So these are the 5 things to think about as I'm going to do this whirlwind tour for you. And yeah, I said my name's Cyrus. I'll leave this up here for a second, and I'll answer just a couple questions before we get started. That's how you can hunt me down. But yeah, does anyone have any questions real quick before we switch gears a little bit? We're good?
I have a question.
Sure.
Does VisIt have a way that you can export whatever you've done to a Python script to do it again, or some other script?
Yeah, so it does have a way to record, and also there is a way to write a script. The best way to do it is to record while you're doing it. I'll show you how to do that. So I'll show it as part of my hands-on stuff. Anything else? All right. Now it's time to get ridiculous. No, I'm just kidding. Okay. All right, so if you've downloaded VisIt, you can just double-click on it. If you have a Mac, there's other instructions for Windows and Linux. And you can also run it from the command line if you're Mac. All that stuff is basically on that tutorial preparation page, shows you how to do that. When you start VisIt up, here's what you see out of the box. So you get one window to start with, which is the viewer window. So again, that controls the state, and that's where we're going to see pictures. And this guy over here on your left, that is the GUI. So that's where you set things up, and that's where you manipulate your pipelines. So the first thing that we're going to do is we're going to open some example data. So if you downloaded the tutorial example data, there's a whole bunch of files in there, but we're pretty much going to look at the obviously named one called example.silo. So if I open that up and I hit OK, nothing happens except for the fact that we've successfully opened up example.silo. So that's by design, so we don't want to start trying to guess what you're going to do because it could be expensive. First thing we'll do is we'll make a plot. So that's one of our first abstractions here. So this here, this plus sign, that's where we can add our plot. So this is our menu of different things that we have available as plotting. We're going to do a pseudocolor plot, and we're going to plot the pressure variable. So all of these variables, there's a whole bunch of stuff in that silo file. All these variables are exposed. So different parts of this menu, for instance, the vector plot might need vector data. So the different parts of the menu are going to look different based on what data is published. But we're going to do pseudocolor of pressure to start. All right, so we have something that's green, which makes us feel like things should be OK, but we still don't have a picture. Well, we have to click draw. So let's click draw. All right, we have our first plot up. Your color table is probably different than mine, because mine is actually set. So let's go ahead and change yours to look a little bit like mine. So this is where all your plots are going to be here over on the left. If you expand this out, you'll get operators and things will come into play. But the way VisIt works in its GUI is it has these attribute windows. So if I double click here on the pseudocolor plot, I'll get access to the things that I can tweak about the pseudocolor plot. So you notice here that I've changed my color table to a different color table, a better color table than the default. It's called spectral, and I've also inverted it. That's a kind of a preference thing of mine, but there's a whole bunch of different other color tables you can pick. And here's where you can also control things like the limits of the plot. So let me rotate this around a little bit. So we have a 3D plot. If you look up here, we have some scalar range of our pressure that goes from about 1 to almost 6. So we can do things like clamp the ranges that we're looking at. So let's do it to, say we want to only look at things between 3 and 5. We get a different scaling of our color bar. If you're using VisIt 3.0, you'll also have these things that will allow you to do, point out where you're actually clipping the data. So that's kind of nice. You can enable this and say if things are less than the minimum, I want it to be one color, and if things are greater than the maximum, I want it to be another color, perhaps shocking colors, so you can see where you're making the estimates. I don't know where the red is. Probably inside. So here's our pseudocolor plot that we made. We can interact with it in a variety of different ways. You can see me here. I'm just doing rotations with my trackball. There's also different modes, like I can pick a particular zone. If I do that, it shows me where that zone is on the mesh, that A there, and then it gives me all kinds of different information about it. We can zoom in. So I can manipulate the view in various different ways. And the most important thing is the reset view, right? So we can get back to where we were. So about what you expect for exploring things. You can also, it's better with a mouse wheel, but I can do gestures and stuff to zoom in and out. So those of you who have VisIt up, I'm about to go faster, but does everyone feel comfortable with this basic stuff? Okay.
Show where the reset is again?
Yeah, sorry. So that's right there. There's the arrows that are going like this. So to show the actual mesh, that's actually a different type of plot. So pseudocolor just as a pseudocolor plot, and to show basically the lines of the mesh, we have something called a mesh plot. So if I add that, we can view both of these at the same time. This will show you the computational zones. And one of the important things that I sometimes forget, but I'm not going to forget, is to show you how to actually save out a PNG image, because that's pretty important. So once you have your beautiful plot that you'd like to set up here, which we'll give it a chance. We don't have to. We're not that proud of it yet, but it's okay. It's worth a PNG file. If we go to File and we go to Set Save Options, so the File menu I clicked on up there. You'll have a bunch of different settings here. You can change the resolution that you'd like to output it to be. It doesn't have to be the same thing as what's on your screen, so it'll render it bigger, for instance. And you can change the file name. Hit Apply and Save. There's a message which you can't see because my head's blocking it that says it saved it to this place. Let's go here real quick. Sorry. And let me just open it up. Oh no, I can't. Oh wow, okay. My Mac doesn't want to open things up. Well, let's browse there. There we go. So there's the PNG image I created. So that was file, set save options. And then similarly, although I'm not going to show this, there's actually a movie wizard that allows you to render out a time-varying sequence. But that's an easy way to get a movie out of VisIt, once you have things set up the way you'd like them. All right, so I'm going to get rid of this mesh plot. Let's start looking at some operators. So again, operators are how we can slice and dice our data. So in this case, I'm just going to do literally that. I'm going to slice it. So here I'm going to add under the operators menu here. I'm going to go to slicing, slice. And when I do that, I now have a 2D plot that basically is a slice of my 3D plot. If you're curious of where it actually sliced, there's some default settings. Again, in the plot list here, I can double click on the slice attributes, and you can see what it picked. So in this case, it picked, y-axis at the intercept, origin 0, and projected it to 2D. If you want, you can unproject it to 2D so you can see where that plane was in the original view. And we could change it, right? Again, everything you change, you have to hit. Oh, that's way out of range. Everything you change, you have to hit apply before it's going to do it for you. So if we did, something like this, we can look at the different. There's also a way to do it interactively, but I'm not going to show you that right now. I'll show you later if you want. When you're in 2D, there's a couple other different things you can do. So one thing you can do is a line out. So there's these squiggly lines up here, up in the top, and this is the line out mode. So if I click and drag, I can get a curve out that's all those values across that line. There's also a way to do this through the query interface where you could actually type in the values. That's usually a better way to do it, but for 2D data, it's not too bad. So notice when I did this curve plot, it actually popped up a new visualization window. That's something that VisIt does often when it's generating curve data because it can't really show them in the same place. It gives you the full controls on another window. I'm just going to get rid of this for now, but something to note. And let's do something slightly different. So we did our slice. We can also slice things by the values of the field. So if I go and add under slicing, I can add an isosurface operator. And that's going to pull out contours. By default, it's going to be set up to just do 10 contours evenly spaced throughout everything. So let's just draw that. You can see there's a whole bunch of interesting structure in there. So there's also something called an isovolume operator, which instead of pulling out surfaces, it will pull out volumes between two isosurfaces. So that's interesting if you want to do things like integrals of mass and things of that nature. There's also, more basically, there's a threshold operator. So if you just want to do, think about it as ripping out all the Legos that are above or below a particular value, you can do that. So if we do the threshold, I did all the ones on the inside, sorry. Let's do it this way. There we go. So if I do a threshold, I'm basically just excluding all the blocks based on their value. Similar to an isovolume or isosurface, but it's not actually changing. It's really just throwing away parts of the mesh. It's not cutting them or cutting them smoothly, interpolating things. All right. So let's look at another plot real quick. Let's look at the volume plot. So this is volume rendering. We're going to add a volume plot of pressure. I'm going to draw that. Now, what the volume plot does, and again, I have a different color table here. What the volume plot does, again, is it's kind of, you can think of it as sending X-rays through your data. And as it hits parts of your data with this transfer function up here, which we're going to mess with, it will attribute color to those rays that go through your data. So if we look at the volume plot, under the transfer function options, this is where we have a histogram here that tells us basically all the values that are in this data set. And we can tweak the opacity of when the rays go through by messing with this. So if I wanted to just draw here and tail off things, I can create something that has a transparent look to it. I can kind of get into my data. And this is what, this is what Joe talked about earlier too. If he had the example that was a mouse, right? If he knows particular density values are particular, part of the mouse's anatomy, like its skin or its bones, then you could really tweak a color table and tweak these transfer functions in order to make a realistic view, or at least something that can conceptually tell, not betray, convey what you're trying to find. All right. So, yeah, so one other thing I want to show quickly is there's something called a subset plot. And this plot does a couple things. Actually, it will show your parallel, it's not going to show it here, but it will show your parallel decomposition. So if you were working with a data set that actually is parallelly decomposed, let me open up one real quick, like this one, multi-UCD. It will show you effectively what things are being, how the things are being distributed in an MPI manner, I guess is the best way to say it. Or this is actually what's coming out of the simulation code. The simulation code wrote them out in this broken up way, and you can see the way that is distributed. So that's a subset plot. Another thing that we have here for all the plots is this Venn diagram here, and that actually allows you to do subset selections. So in this case, there happen to be a whole bunch of different chunks or domains. If we're debugging problems, we can turn particular ones on or off, and really dive into what's going on here. This is really useful if you have a simulation code and something's crashed. You don't want to read your whole data set in. You draw the plot, or you put the plot up, but before you draw it, you go into this subset thing and you turn off all the stuff, and everything's wired up right with a silo database or something. You'll only read in the parts that you actually care about. So if you know there's a crash in some part of your problem, helps you a whole lot. So that was just a couple plots, a couple operators. Let's go ahead and let's go to look at expressions real quick. So something I haven't showed that much is the controls menu. So there's only a couple places to go to in VisIt. There's a whole bunch of buttons to pick on the GUI, and most of the rest of the buttons are here in the controls menu. So this is where we can get to our expression editor. And again, our expression language, or a little DSL, allows us to compose things on the fly from existing fields and make new fields. In this example, we'll do a gradient of we'll do a gradient of the vector field that happens to be in this data, and then we'll be able to plot that a couple different ways. So to create an expression, I say new, I give it a name, so I'm going to call it my grad. Might be hard to see. I need to tell it that I'm dealing with a vector, and I happen to know it's just called gradient, if I can spell. But if I didn't know that, there's this insert function here that would allow me to search through all the different menu of things that VisIt provides. In this case, I'm going to add my, let's see, what am I going to add? Oh, actually, I'm going to take the gradient of the pressure, and I'm going to take the gradient of the pressure itself, not the velocity. Velocity is already 3D. So okay, so I defined something. If you can't see what I said, it's called myGrad, and it's a gradient of a pressure, and that gives me a new vector field. I'm also going to define something that shows me the magnitude of that. And that's going to be a scalar. And from here, after I do that, I'll find basically my new variable will appear as something that I can plot. And I can. And what it does, it's not in the database, but on the fly, it will calculate that for us. Similarly, I created a new vector field. Now I can plot that with my vector plot, which we haven't seen before, so let me show it to you. By default, so the vector plot uses glyphs. You can think of these as little arrows or little circles that it's putting at all the points of interest. By default, it's really tuned down so you don't accidentally try to render a bazillion glyphs, because glyphs are more expensive. So for this example, we'll just set some stride. That means plot every x of these. So I'm going to plot every 11th, and I'm going to draw it. And it's going to show these little glyphs. We can tweak different things about this. We can make things bigger. But just to give you an idea, make them really big. Now this is basically the vector field that I created, which is the gradient of that pressure variable. Last thing are queries. So let's go ahead and do something with that very quickly. So let me go back to my pressure. If I go to controls again, there's queries, which is a huge menu of things you can do. And that includes, things like, simple things like the maximum. So let's just do that. So I scroll down to something called max. And I hit query, and it'll tell me, hey, your maximum pressure is this value, and it's at that place and that node and all kinds of great stuff. Similarly, there's min. I could find out where the minimum pressure is. Again, these are data summarization operations. There's also things like variable sum, which will do basically add everything out. You can think about that. So by slicing and dicing your data, moving things around, then you can get to a point where you can ask different questions based on how you've manipulated things. All right. So I showed you how to save a PNG file. You can also just save your whole state to something called a session file. So under the file menu, there's something called save session as. And effectively, if you do this, then you can go back and load up all your plots and all that stuff from a simple file later. So that's handy. That's a handy way of pulling your work back up. Now, all right, so we're getting close to the end of the basic tour here. Last thing is Python. So I want to show you how to use Python. So VisIt ships with the Python built into it. And it has this Python command line interface. That's what we call it, the CLI. So when you start VisIt, there's a bunch of different ways to do it. But one important way, which I'll show you, is you can run VisIt with -nowin-CLI. And when you do this, VisIt will not pop up any windows. And you can then run Python commands inside of this. So this is how you would run in, say, batch mode. If you have a script set up, you could hand this to like a batch mode job. It won't pop up any windows. Nothing bad will happen. You can save pictures out and things of that nature. For the purposes of this tutorial, I'm actually going to just be showing you how to run the Python command line interface from inside of VisIt. You can also do that. So we're going to go to the controls menu, and we're going to go to command. So what this is basically a whole bunch of different little scratch pads for doing Python. And it's also where we can record things that we do in the GUI and make them into Python scripts. So I'm going to run some examples first, which I've already programmed in here. I'm going to show you those examples, and then I'll show you how to record your own stuff. These examples are also on the wiki page. There's a tarball that has the simulation scripts that you can play with. The way to think about this is that pretty much anything you can do in the GUI, manipulating databases, plots, operators, things like that, you can do that from the command line interface. So we're going to show a couple examples of that. So the first example is the most basic. And this is kind of the first thing I showed you. I set something up and I pegged some mins and maxes in a pseudo-color plot. So to do that, we call add plot. We draw the plots themselves and we set some attributes. So these things here map mentally to what you found in the attributes window. And you can also print these things out in Python to see all the different things that you can change. So let's go ahead and run that. I have this set up to make it easy for me to run these without having to paste things in. But we're going a little bit faster, so just bear with me. So I'm going to run the first listing. And all this is really doing is reading in the Python script and running it. So it starts up the command line interface. Oh no. What did I do wrong? Oh, I'm in the wrong directory. All right. So it doesn't make it easy for me. Let's start VisIt here. Get my example data set back up. Okay, so this particular script assumes that you have the example data set already up. Command. All right, let's try this again. Okay, so execute this. Oh no. All right, here's what we're going to do. We're going to cut and paste it in there. No. Almost got it. That looks right. Yay. All right. We're in business now. Okay, so we created our plot. We tweaked some of the min-max values. That's great. So that's the most basic example we can do. Let's take a look at something a little bit more complicated. So this example here, it also creates a pseudo-color plot, but it adds an isosurface operator. And then what it does is it sweeps the isosurface value across the data set. And yeah, so in this example, I'm not actually going to save off a whole bunch of PNGs, but the way you would do that in the future is you would uncomment this. So save window is equivalent of going to that file set save thing that we saw before. So if we run this, we expect to see a plot, and we expect to see these ISO values animate across through the plot. So let's run number 2. Let's get this out of the way so you can see it. So now you can see it animating through the ISO values. Again, just a simple example. All right, last Python example that we're going to show you, which is my favorite. So this example it's pretty short. It's about 50 lines, and it shows you how to use all the different things that I talked about. So it sets up a pseudo-color plot, and it adds what's called a 3-slice operator, which is not an operator we saw, but it's basically something that does these orthogonal slices. So we use it to make kind of like a little diorama around our data set. So that's this. Then it actually queries to get a maximum value to demonstrate that you can query from Python and how to do that. It prints it out. It defines an expression to take the gradient of our temperature variable, which we didn't look at, but it's another variable in the data set. In this case, it adds another pseudo-color plot that actually creates streamlines. So streamlines are done through an operator in VisIt called an integral curve operator, because it's integrating across these vector fields. And then finally, it sets some style. So that's a lot, but it's a pretty concise script. It's showing you how to compose all these things together. So let's go ahead and take a look at it. And for good measure, we'll execute it a couple times because it might yell at us, persist. And so here we go. So we ran that, and you can see our 3-slice in the background. Again, that's the diorama thing. And then we took a vector. We didn't have this vector field before, but we took the gradient of the temperature, and then we did a streamline integration across all that. And so you can see where kind of the critical points are in this. Okay, so that's the basics. The other thing, which I should show you, is how to connect to Cooley. Let's do that super quickly. So once you have things set up, which you probably won't outside the box, there was an option to select different host profiles. If all went well, you will have this option. If not, talk to me later. But when you go to File Open, so I was just browsing on the local file system, but I also have the option to select a different host. In this case, I have Cooley set up. My username on my Mac laptop is not the same as my Cooley username, so I have to click this box here that says change username to my actual username. After I do that, and there's a way to set that in the settings too. After I do that, it's time to use our token. No way I typed that right. Oh, I did type it right. Okay. Whew. Applause, please. No, I'm just kidding. Okay, so now I'm browsing on the remote file system. So I have some data that I just have laying around here, right, from before. Just open that up. After I do this, it'll ask me what parallel options I want to start up for Cooley. I'm going to cheat and just run in serial on the login node because I don't want to wait. Even though you've greased the skids for me, we're just going to do something for 2 seconds here. So just start a serial engine. And now I can read the data on Cooley and I can render it, and then it'll come across, and I have my data set. So this is actually the aneurysm data set, which we're going to look at. Quickly, any questions? Yeah.
So is that launching a job on Cooley?
It is. In the case I did, it didn't actually, but there was so serial doesn't do that, it just runs on long, but there was batch, and the batch one would launch it. And there are similarly the options for the queues and all that stuff. Everyone okay? Ready to look at some other stuff? All right. So we're going to switch gears here, and we're going to look at some simulation data. The first one we're going to look at is the potential flow simulation, and this is it's a very simple data set. It's written, with basically what it is it's looking at flow around an obstruction. In this case, a very small airfoil. Again, it's very simple. This model basically says, hey, there's no rotational motion. It's not the best model, but it's great for teaching people how to learn how to use MFEM, which I'm not sure if they're going to show you the code tomorrow or not. They may. But if you're going to do a lot more crazy hydrodynamics and things like that, you need to go further and do better math. But for our purposes, we have this data set, and we're going to explore it and just look at it in VisIt. This data set isn't time varying. It's really a set of a whole bunch of different cases where they varied the angle of attack. So there's, you can think of it as the flow is either going straight on, or it actually starts a little bit below and it goes a little bit higher. We group them together in VisIt. So it looks like a time series, but it's not a time series. But the way to think of this is basically some state space that we're covered with a whole bunch of different solvers, not necessarily a time varying simulation. So let's go ahead and get started with that. Let me get VisIt up again. So we have if the tarball that if you downloaded it, there's a file called potential flow ang sweep.visit. That's really just a simple text file that groups together a whole bunch of VTK files to make it easy to open them up all at once. So if I open that up, we can start exploring this. First thing we want to do is take a look at the mesh itself. So if we draw that, we can see that this is structured or unstructured. It's definitely unstructured. It's a whole bunch of triangles, and it's pretty highly refined if we get down here. So that's what we're solving on. We can play with the mesh a little bit to make it look a little bit different or explore different aspects of it. So if we want to draw the mesh itself, with a different color scheme or something like that, we can do that. Sometimes this is useful if you're going to draw streamlines or something on top of it. You still want to have the mesh to look at. Sometimes it's just too much noise. Depends on what you're doing. So that's what the mesh looks like. It also has a couple fields, but in particular, it has the velocity, which is the thing we're going to care about for this potential flow. When you publish a vector field to VisIt, it automatically defines an expression for you that allows you to look at its magnitude. So that's handy. You don't have to go in and define your own magnitude expression. So we're going to take a look at that. In this case, the velocity vector field is called V, very creative, but also very concise. So we're going to draw a pseudo color plot of that. And one of the aspects of this is things get a little crazy with the velocity field in these very, very small zones. So to give us a stable basis for all these different cases, I'm actually going to pin the upper limit of the pseudo color so the color bar just doesn't jump wild all over the place. So it's a fancy way of saying I'm going to check this box here and say 1 should be the maximum. We'll go ahead and set that up on our plot of the magnitude of the velocity, and we can draw this now. Now in this case, our mesh is probably getting in the way of what we want to see. So I'm going to hide it. And we have here our different cases, right? So this is the velocity magnitude. So the different cases, as things hit the airfoil boundary in different ways, they respond differently. So if you look up here, it says time, but it's not really time. The time is actually the angle. They kind of hacked that in there. So if we go from -5 all the way up to to 25, you can see you have all these different cases here with what's happening with the vector field. Now, we're not looking at the vector field directly, so maybe this isn't very intuitive yet, but we're getting some information out of it. We can also look at contours of this. So let's look at the contours. So I can add on top of this a contour plot. So let's do that. Let's look at the velocity magnitude. Again, I'm going to peg things to be a maximum of 1 just for consistency across all these time steps. I'm going to draw this. Okay. So now we're looking at contours of fixed velocity magnitude. And again, we can see things are changing quite wildly, quite differently for all these different cases. Make sense? Okay. What you probably want to do is look at the vector field directly, right? So let's do that. I will caution you, though. This is what the mesh looks like. Those vectors are all hanging out on this mesh, so it might be a little bit noisy to your visual system. But we'll plot them, and we'll try to get something that helps us confirm what we think is going on in this simulation. So to draw a vector plot, we go add vector, and again, it's called V. And we're going to have to tweak a whole bunch of different settings here. Again, VisIt's programmed to not let you shoot yourself in the foot with this, fixed. It gives you a fixed number of vectors. We're going to change that to a nice prime number for good luck. And for your case, we're also going to change the color table to Viridis, so that'll be different. So if we keep the same color table, we might not be able to see the vectors also with the pseudo color behind it. And we're going to tweak a couple other things. We're going to take off scale by magnitude and auto scale in the glyph section. And this is, again, because some of these vectors get really crazy around those small places. So this is just to give us a consistent view of the vectors across all of these time steps. I'm actually going to delete the contour plot because I don't need it. And let's go ahead and look at our vectors. Okay. So let's zoom in. So near the airfoil, things are changing. Away from the airfoil, things are relatively the same here, following the same angle that you would expect. So if we drag, we'll be able to see things. We're going from -5 up to 25. The reason why the color is changing is, again, because I forgot to click something, but the magnitudes are changing. So if I can limit that as well by setting this to 1. And then they'll all have a consistent color. So again, away from the airfoil, we expect our static field to just be whatever the angle is inputted. Near the airfoil, well, that's where the solver is helping us, right? It needs to do something. So it needs to deal with it. So we get more complex behavior. Again, this is a little bit noisy. It's kind of hard to look at glyphs sometimes. So you can you can try to make it more sparse, things of that nature. Now, what's probably the more intuitive way to think about this? Does anyone have an idea? We can do streamlines. So streamlines should tell us if we actually put some dye, at a particular place in this, where that dye would go, right? It's analogous to actually being in a wind tunnel or something like that and setting out little strands of smoke across this. So let's go ahead and let's set up some streamlines. So in VisIt, a couple versions ago, we used to have a streamline plot, and it was its own plot. And we took that plot away. And the reason why we took that plot away is because what the streamline infrastructure itself is really this complicated thing that I'll integrate the streamlines for you. And you might want to use them with all kinds of plots, right? So we took that away and we made it an operator. And the operator is called the integral curve operator. So what we'll do is we're going to set up a new pseudo color plot that uses the integral curve operator in order to show us the streamlines. And we expect to be able to put some over on the left side and then see what happens, across the airfoil. I'm going to delete this vector plot so it doesn't get in our way. Keep our velocity magnitude plot. And I have my cheat sheets here so I can type the right numbers, but you also have the manual if you'd like to type the right numbers. So again, I'm going to add a pseudo-color plot. From here I go to operators, integral curve, and I'm going to take an integral curve of the velocity vector. Integral curve has a lot of options. So when you're seeding the streamlines, you need to say where to put them. So there's all kinds of different ways of thinking of setting them around the data set. So there's a point, a circle, a line, box of that, all those kinds of things with what, kind of intuitive what you would think. If you're doing a point, well, it's an XYZ space. If you're doing a circle, you'll have options for how it needs to be oriented and how many samples around the boundary and stuff. In our case, we're going to go with a line because due to the nature of this data set, we know that the flow is going from left to right. And we're just going to seed around this part here on the left. Yes, sure.
Why would you go to the add the operator versus the operator option next to the add?
Yeah, so this operator is a special operator in that it creates sort of its own field as well. So that's why you do it that way.
So for a lot of these, like for fluids, we know that we're going to have a streamline as an aspect. So the data will most likely have that already inherent too. Or to have that within it.
What do you, sorry.
I guess I'm just wondering, like the operators, like for certain types of visualization, so for fluids, we know that streamline is a typical operator.
Yes.
So the calculations might be done beforehand so that we just look at it via add.
Oh, do you guys have, so you're putting out your own streamlines or?
No,
Okay.
that's what I'm wondering about.
Okay.
It's like why it's under add, so it's already within the data?
No. So okay, let me show you. This is confusing. Maybe we should bring our streamline plot back. So when you add it in that manner, effectively it's adding the new operator for you, and it's going to be plotting the output of that operator, which is the streamline itself, not the original data set.
But what about the operator option versus the add?
Yeah, so you could go in and you could manually add this under integral curve, but then you'd have to change a variable back up at the top. It's complicated. So this is the one place where it is definitely not intuitive, but you have to learn this simple pattern, and it's there on the web page too. So once.
I guess my question
Yeah.
then is really like with the operators and adding it, okay, never mind. I think I got it.
That's okay. I mean, this is a confusing aspect of things. It's a little different in that it's not just generating new data or not just clipping things. It's also creating a new field. That field happens to be like the time across the curve, if that makes sense. So it does a lot more.
Got it. Thank you.
Yeah, no problem. So we're gonna select seeds for our integral curve, aka our streamline, and we're gonna do this line. So we'll go ahead and put in the the pre-thought of values here. So we're going to basically pin it at -2, and then we're going to sample it in the vertical, -2x, and then we're going to sample it in the vertical direction. So I'm going to start at -2, -2, and then I'm going to end at -2, 2. And along this line, I want to do 10 seeds. I'm going to hit apply a lot of different times for good measure, because VisIt tends to be stubborn sometimes. And when we do that, we get our initial set of streamlines here. The streamlines themselves are, basically you can think of them as little tubes. There's options in the pseudo-color plot itself in order to draw the heads and tails. So if we open up the pseudo-color plot and we go to geometry, we can enable the tail, and we can also make it look fancier. So we can turn it from lines to something like a ribbon. Let me just do that. And there you go. So, and the spheres are way too big, so let's change those. All right. So there's our streamlines seated there. And, again, this isn't a time-varying simulation, but it's a whole bunch of different cases. So we can just drag across and recompute the streamlines on the fly for any of the cases that we want to. So that we expect to be the highest angle, that we expect to be under, If you want to have a lot of fun with it, you can see when at one angle this particular streamline flips from the top to the bottom, things of that nature. You can generate different. This particular thing here, it's colored. The streamline itself is colored by the time, but you can put other things on there. You could put a random seed, things of that nature. Those are actually in the integral curve operator options. So arc length. There's all kinds of different stuff you can select. So probably, seed point ID is a decent one, right? If you wanted to track them for some reason, it's just going to give them, 0 to 9. I have 10 of them. But yeah, and you could also export these. There's different ways to crop them and things of that nature. Now, streamlines themselves, they assume like a steady state solution. So given a vector field, you're going to advect it infinitely, and that's the streamline that, infinitely, that's the streamline you're going to get. Pathlines, on the other hand, actually will take a time-varying data set and they will advect it, you can think of it per time step. We don't have a time-varying data set. We could try it and see what happens. What do we think will happen? I haven't done it yet. This is very dangerous. But let's see what happens. It's just going to crash hard. It's reading all the files. We have to have a spectacular failure before we move on, right? Okay, it's working. Might take a while. Any questions while we get this really bad answer that we're about to get?
How did you get more than one streamline?
Yeah, so here, under the integral curve operator options, I set up basically, you can't see it at all. Maybe that's better for you. So I set up a source type that was a line. And so you can think of it as I stretched a line out, and then I told it I wanted 10 dots along that line. Does that make sense?
Yeah.
Okay.
Thank you.
Yeah. And again, you can do boxes. You can do all kinds of stuff. Hey, look, it finished. I think it finished. It did. So what did it do? It did what I expected it to do, but we had angles bending like this, right? Just slightly bent things. In a real-time varying simulation, a pathline is useful. This is not necessarily useful here. Other questions? Yeah.
Yeah, so this is like a velocity field, right? So
Yes.
And how does it calculate then the streamlines? Is it trying to follow some gradient or?
So it uses, yes, it does. Well, if it's a streamline, it will just use the velocity field directly and do like Rangakata or something like that. If it's time varying, it will basically look at the two steps of the mesh and figure out a gradient basically figure out the difference between the vector fields across the mesh. And for the, there's options for integrators and all those things here, right? So including some that are very specific to certain data producers. But typically, the dormant prints, the default works pretty well. You can say if you want to go forward or backward, and you can clamp things and all stuff like that. Yeah. But in the pathline case, it's going to actually do a mesh to mesh mapping, and then, yeah. All right. We're almost there. We've got to make sure we leave room for our 30 seconds of questions. No, I'm just kidding. Let's take a look at another data set real quick. So this data set is the aneurysm data set. Oops. And this is a 3D data set. I'm just going to throw up a mesh plot of it real quick. Oops. And yeah, so this is actually a time varying data set. So it's blood flow through this artery where there's an aneurysm. So we have things like the pressure and we have the velocity vector field in it. So it's a little bit more interesting than our airflow over our flow over an airfoil. So we have a decent amount of time. So we'll walk through some of the steps of this. The first question is, all right. So here's our mesh. What type of elements are used in this simulation by staring? Just the quiz. What do you think? It looks like triangles, but it's volumetric. So what do you think? Tets, that's right. So we're just seeing the outside of it. If we wanted to see all the gory details, we could go into the mesh plot and we could tell it that we want to turn the opaque mode off, and then we'd see kind of all the way into the data set here, which becomes quite a bit of a mess if you zoom way out. Oh wait, no, I need to do internal, yeah. Show internal zones, sorry. Yeah, so there's all of our TETs. So this is simulated on these TETs. The mesh itself is fixed in time, but the solution evolves on that mesh. So the mesh isn't going to be very interesting to animate. We'll have to look at the fields. So let's go ahead and take a look at a couple of the fields. So the first thing we'll look at is the pressure. I'll draw that. And here we are. And if we animate this, or we push play, we'll see things are changing. So I just let the color bar float here, but just, we could pin it in something to make a better picture. But this is showing that there is pressure evolving in this simulation. It's about 200 different time steps. There's silo files, which is a format that we use at Livermore a lot, binary files that are pretty decent to hand around. So there's about 200 of them. So I just animated the whole thing. Now, when you're thinking about the heart, what's sort of the canonical thing you think about when you think about a heart? Or something that if you go to the doctor, or if you blood pressure or something. Okay, that's a good one. What about, what's that?
Like pool where there's flow stops.
So-
Small points where the flow might stop or rotate.
So that would, that's bad, which is probably going to happen. So we'll look at a little bit of that. There's some bad things happening in this aneurysm, obviously. What's the, all right, I should say it better. What's the canonical signal that you think about from a heart? Heartbeat, okay, thank you. So I was, the pulse, yes. Sorry. Very good answers, though. I need to be more. So if we're simulating an aneurysm, we would hope that we're simulating it with something that's physically meaningful, which means there should be some signal of a heartbeat in here, right? Can someone think about how we might try to figure that out? So we have different things that we can ask questions with in VisIt. So
Frequency of pressure.
integrate the pressure, okay. So that's good. We're going to just take the maximum of the pressure because it'll do it as well. But we could also do something like that. That would be a more quantitative way to do it. So to do that, we're going to use a query, number 5 on our 5 things to know. So I go to Controls, Query. Before I do this, when we created this silo data set, we didn't write the timeout in it, unfortunately. So we're going to go to our, well, actually, we did write the time, sorry. We have the time, but by default, the query over time will look for a cycle, which is really just like a physics counter. We don't have a cycle, and by default, the query over time is going to create an x-axis with that cycle, and we're going to get a straight up, vertical line, which is not that useful. So I'm going to set my query over time options to instead tell it that we'd like the time to be used. And now from here, we're going to just look at the max. This is something we did before, but we're going to do something a little bit different. We're going to enable this time query. And when we do this, it's going to do that query at every point in the data set that we have it, or we can do some stride if we want it to go faster. And then it's going to give us a curve. Right? So I'm going to cheat, and I'm going to take every 10th step, because we're running a little bit low on time. I'll hit query, and now it's frantically reading 200 different files, doing this query, almost there, and we get this. So there's our maximum pressure that we extracted just from the pressure field. So how many heartbeats do we have? 2-ish, yeah. If you wanted to, you could go in and say, okay, what's the frequency or something like that. All that information's there for you. So that gives you an idea of how you can kind of ask course questions and get something anchored there. Sorry, I gotta get my cheat sheets back. So the other thing that we have is we have the velocity. So this is a fluid flow simulation. Oops. So let's take a look at that. So if I go and take a look at the velocity magnitude, again, I have a vector field. VisIt will automatically create that scalar expression for me for the magnitude. And here we are. We have our velocity vector field, and we notice that nothing's really happening on the boundary, which is probably a good thing. You want all the fluid to stay inside, except for this inlet here and this inlet here. And you can actually, if you watch it over time, you will notice that the flow changes. Particularly when those heartbeats hit, you'll see things change. But looking at velocity, there it went. Looking at velocity in this way it's not telling us that much, right? So because it's all the structure is internal to this data set. So how can we look inside of it? Anyone have any ideas?
Make slices.
Slice is a good way. So we could try to do that. This can be a little hard to slice, but let's try to do it. So let's slice it at x equals 3.8. Sorry. Cool. It's actually projected to 2D, so we're only seeing a 2D part of it. If we actually wanted to keep the volume, we would use a clip instead of a slice. There's a clip operator, so we can keep the other half. But let's just take a look at this slice for a little bit here. Push play, back. So now we can see more structure. That's cool. Another way we can look at it is we can look at isosurfaces inside of it. So when we do that, we probably don't want to look at a whole bunch of isosurfaces. We want to just look at where things are moving quickly. So I'm going to go ahead and I'm going to add the isosurface operator. And I'm going to use my cheat sheet here, which are a few values that I know happen to be high, 10, 15, 20. And we're going to draw this. Now, I'll play, and we can take a look at it here. And you can say, OK, we can see where things are going on, but we're kind of lacking a little bit of context here from the original mesh. So we can solve that by putting a mesh plot up that's sort of transparent and having that mesh plot be there while we're looking at these isosurfaces. So let's do that. In order for this to work, you have to uncheck this box here that's called Apply Operators to All Plots. By default, if you set up a whole bunch of plots and you add, say, an isosurface, VisIt will add it to all of them with all the same settings. In this case, we're going to create a plot of the mesh that sort of serves as a background, so we don't want to cut it at all. We just want it to be there. So to do that, I'm going to add a subset plot of the mesh. You could also just add a mesh plot and tweak a bunch of different settings. Again, the subset plot just kind of shows a single color. I'm going to select something here, and I'm going to turn the opacity down. And I'm going to draw. So we can see our original mesh now. Again, these steps are on the tutorial page, so I know I'm going fast, but they're there. So now we can have a little bit more context, right? And we can see this is where things are flowing a lot, right? And we can see it kind of surge whenever the heartbeat happens, and we get another heartbeat coming in towards the end. So again, these are isosurfaces that we're looking at. So if I zoom in here, if I can do it right, you'll see that they're surfaces. We could also look at an isovolume. So again, isosurfaces look at your field value and they give you a surface of where everything is 10 or where everything is 15. An isovolume will allow us to look at everything between, say, 15 and 20. So let's switch our isosurface off and add an isovolume instead. So under operators, in this case, the isovolume is under selection. We can set our lower bound and upper bound to 10 and 20. And now we've extracted a subvolume. And I could integrate the amount of volume and things like that. So that's the difference between an isosurface and an isovolume. Depending on what you're doing, you might want to use one or the other. So see it moving all around. So again, we did all this. We haven't looked at we've been doing stuff with the vector field, but we haven't looked at the vector field directly. So we can look at the vector field directly. So let's do that with our vector plot. So I'm going to add a vector plot of velocity. I'm go back to this having to tell VisIt that I'd like it to show me more vectors. And I'm going to do a couple things here with basically setting things up to make them look a little bit better. So under the glyphs here, I'm going to make them a little bit bigger. We're going to use a cylinder for the tips, and we're going to draw it this way. Draw. So now, I also want to change the color table. So the color table is under data. I'm going to change it to Viridis. Okay. So now we can directly view the vector plot, the vectors of the field, and we can watch them animate over time. It's actually a little bit more intuitive here, I think, than in the flow over time, because flow over time, the mesh was so unstructured, it got pretty messy. If we watch this, we can see things are definitely moving faster, moving through, but there's also this dominant flow, right? Things are just continually moving in that direction. So that's the overall general direction of the blood flow. Things go bad there whenever we start to get pulled up into this bubble that probably shouldn't be there. Okay, so again, we can view these glyphs, or we could put streamlines in. So let's put streamlines in, and this will demonstrate also the difference between path lines and streamlines. Before we do that, we know we need to have some place where we're going to seed those streamlines. So where do people think we should put them? We can put them anywhere, but there are probably better places to put them. So sorry, what's someone going to say? In the inflow. So we want to put them, say, here, right? So, but we don't know where that is. We could guess, but we could also use VisIt to help us find out. So let's use VisIt to help us find out. One way we can do this is we can do a slice sort of in this area of a pseudo-color plot, and then we can basically ask for the center of that slice, if that makes sense, or ask for some point on that slice. So to do that, I'll create a pseudo-color plot of our pressure, and I'm going to add a slice operator, and in this case, we want our normal to be, let's see, what are we doing here? Oh, we can just do a point slice. That's the easier way. So we know we want something close to, happens to be, I mean, it doesn't matter, but we're going to have a plane here, but we're just going to say 333 as a point slice. We draw that. Oh no. I got to uncheck the project to 2D or it yells at me. Okay, so I did my slice, and okay, here's our part that we care about here. Let me actually change this to the velocity magnitude, and what we'll do is we'll query this, and we'll just look for the maximum velocity magnitude on this little slice here. So we do that with our query, and on my query, you'll notice there's two options here. There's original data and actual data. That allows you to toggle basically between the data that came out of the database and whatever you've done to it. So I usually use actual data. But in this case, I'm going to query the max, and it's going to tell me a point. Oops, did I do time query? Oops, I shouldn't have done that. Let me go back. So in this case, I get a point in space, so that where the maximum velocity of the magnitude is that's on that plane. If I actually if I had original data on, I'd get someplace else in the mesh. But usually you want to use actual data. So here we go. We have a point in space. It's 3, 3.5, 3, 5.5. And we can seed our streamlines around that point as the inlet. So let's go ahead and work on our streamlines. So again, pseudo color plot. This is the most confusing part. Operators, integral curve, velocity. From here, we're going to set up our seed. So in this case, we'll use a circle. You have to think a little bit in 3D here. We know the point where we want it to be at, 3.5, oh, 3.45, 3, and 5.5. And in this case, you have to trust me on this, but our normal and up are these values. So that's, we're putting a circle in space, but we need to orient it correctly as well, because it matters for which way the streamlines will be advected. If we got it wrong, we could reverse it. And we're going to sample along the boundary and do a bunch of different points. Just click draw. Critical points, that's fine. Forgot to set the radius, it was way too big. Yay, okay. So we got our streamlines. We want to make them so we can see them better. Again, those are that's in the pseudocolor plot attributes. In this case, we want to put a cone at the end of it so we know which way is which. Let's take a look at what that looks like. Great. Okay, so now we have our streamlines. Again, streamlines are, fixed in time. I'm going to disable, there's a warning here. So when you're advecting these things, you can get into bad numerical situations. And it happens, you run into a critical point or something like that. VisIt will yell at you because it wants you to know things are happening. We don't want it to yell at us too much. So we just turn all these things off during our tutorial. But it's handy to know when some bad numerics is happening. But really what we're doing here is if we look at these streamlines, we have this time varying data set, but we're only looking at we're pretending like it's advecting them through the whole time. That's not quite correct. So what we'd like to do is we'd like to figure out if we actually seeded them there over the time of the simulation, where would they end up? And to do that, we have to do path lines. So we go back to the streamline or the integral curve properties, and under appearance, there's something called path line. Now, there's let's see here. Yeah, there's a couple of there's some caveats here. What I talked about earlier, how you have to map meshes onto each other, and that can be expensive. In this case, the mesh isn't moving at all, so we can just diff the velocity vector fields directly. So there's a special case here for doing that. We can change that to say the mesh is static over time. When we do this, we'll get a much faster answer because it's not going to actually have to do mesh-to-mesh mapping. And we'll get something that allows us, if we start at the beginning of time here, we'll get something that actually shows us if at the beginning of the simulation, if we put these 12 little points around where the data would end up. So you can see some of it gets entrained up in there, actually quite a lot of it. Some of it ends up going out the inlet. There's examples, so you can do scripting, so you could crop the streamlines away and make fancy movies and all that, but we'll skip that. We actually have probably about 10 minutes left. I think we'll go ahead and move to questions, and then we'll get you back to caffeine or chocolate or whatever. But be happy to answer any questions real quick. I shouldn't have said caffeine and chocolate. Or is there a break after this? Or yeah, okay, good. We all need it. Well, we'll go ahead. So I'll be around tonight. I'll also be here tomorrow. In particular, the folks in the numerical library section actually need to be here to help out a little bit in the morning if you want to see some of your data coming out of those libraries. But I'd be happy to answer your questions tonight about any VisIt woes that you have. Again, visit upon me your bugs. And if you have any questions about how to visualize or how to think about your data, I'd be happy to help you. So thanks. All right.